Good afternoon. I'm Yuhao from Altair Engineering. Today I'm hosting this webinar with GoEngineer to talk about Inspire sheet metal optimization. So what is Inspire? Inspire is a generative design and optimization tool for design engineers and product engineers. It helps users to design concepts very quickly and easily, and it helps designers to make lighter product, design the product faster, stronger, and also more affordable. Some history about Inspire. Over the past 3 decades, Altair has been the leader in optimization solutions, and it helps customers to implement simulation in the design cycles to create innovative and lightweight products. In 1990s, Altair began developing the commercial application for topology optimization based on some research. In 2000, Airbus utilized Altair's technology called OptiStruct to optimize their wing ribs. This technology helped Airbus reduce 40% of the mass from the wing rib, that is 1,100 pounds. Altair packaged the optimization solution into a more user-friendly interface called Inspire, and make the technology available for designers and design engineers. In 2010, Rockspace used Altair's technology to design this antenna bracket for satellites, and is 3D printed. So some customers of Inspire, it covers a pretty broad industries like aerospace, automotive, heavy industry, and consumer goods. Not all the customers are that sensitive about lightweighting, but like heavy industries, but they are still using Inspire. The reason is Inspire can help them to shorten the design cycle. In a traditional product development process, engineers come up with the concept, then do the detailed design, and after that, the design will pass validation or virtual testing. During this process, a lot of problems will be identified, and then the design has to be modified, and there are multiple iterations in this cycle, and takes a lot of time and money. With Inspire, engineers can come up with a good concept at the very beginning, so it can save a lot of time in between the detailed design and the validation process. How does Inspire work? User first define a package space for the product, then apply some proper load, and Inspire will give the optimized shape of the structure. And based on the optimization result, user can create detailed design of it and validate it in Inspire as well. Also, Inspire provides products to simulate mechanism, kinematic and dynamic systems, optimization solutions, stress analysis, and also manufacturing process simulation. Today I'm going to do a little demo to show you how to use Inspire's technology to optimize and redesign a battery tray for car. On the left hand is a baseline design, and on the right hand is optimized design. The optimized design saves weight by 35%, and it still meets the performance requirements, that is safety factor greater than 1.5 and first model frequency greater than 40 Hz. This is the interface of Inspire. It can read multiple formats of the CAD geometry, like some general CAD like Parasolid or Step, and some original format like UG and CATIA, SolidWorks. So here is original design or previous design. Now we are going to use this as our baseline and create a better design from it. The first step we are going to do is to check the performance of this baseline design, so we can check if there is room for optimization. First, I'm going to extract a mid surface to represent this geometry. It's in this geometry panel. With a few button click, I can get the mid surface very easily. Here you can see it's now all surfaces. And then I'm going to constrain this geometry with fasteners. Here, also with a click, I can build the fasteners. For the loading, because I'm going to apply some G load, that means I need to represent the battery mass somewhere, even though I'm not modeling the battery. I can put a mass here. I'm having 80 kilogram for that. You can translate this mass by dragging the arrows here, or in the panel here you have the exact XYZ coordinates for it. Now I'm touching it to, I'm assuming this battery is sitting on the bottom side, and there is a strap going through those two holes to fasten it. Then I'm going to apply some G load. I'm assuming 5G vertical. Okay. And a 3G fore aft. And 1G lateral. And I need to organize the load to different loading scenarios. Currently I only have one load scenario. Add to another. For the fasteners, they are going to be active for all three load scenarios. And for the G load, each load scenario has one G load. Then after click analyze, I can get a result from it. Also, I want to have the mode frequency, so I request normal modes, like first 3 normal modes here. After click run, it will give me the result. This model already has the result, and you can see under vertical 5G load case, the minimum safety factor is 1.9 here. You can also view the envelope result, including all 3 load cases, by this result envelope. For the model frequency, the first mode is 43 Hz. It's above for requirement, and you can view the animation of it. So the next step we are going to do is to conduct the topology optimization, which will help us determine where are the best place to cut those holes. We need to fill those holes first so that we can let the solver know where it can utilize the space. Inspire provides very easy to use tools to simplify the geometry. By single button click, those holes are filled. And we notice high stress or low safety factor was here. I'm going to fill this space to see if Inspire want to utilize it. You can see how easily I can modify the geometry. Now we create the package space and tell the solver where it can put material. I multi-select panels to allow solver remove material from this package space. We call it design space. And it always this brown color. With this setup, I can start a topology optimization. Select topology, maximize stiffness, or I could minimize mass, but I'm using maximize stiffness here, and certain material to stay after the optimization with minimum frequency of 40 Hz for the first mode. And with this run click, Inspire will optimize the shape for me. Here is the optimization result. We can review it here. And we can drag this bar to have a little bit more material and a little bit less material. It showed me the importance of the material. Like on the very left hand, the material is the most critical one. I'm staying at the middle for this bar. And you can see the first mode frequency is 44 Hz, still above our requirement. From here, I could either export this geometry to a CAD tool, and you can do the detailed design in the CAD, or I can do some simple geometry modifying using Inspire. Let's switch back to this full space, and I'm going to show you how easily it can create some simple geometries. For example, we want to represent this cutout here. I'm clicking this space to draw a box. And then when I switch back to the full space, I can boolean the original sheet with this cutout piece. Now you got a cutout here. By similar operations, I create the concept with topology result in mind. This one shows the concept design with the topology result. And now I can check the performance of this concept by the analyze here. In this model, I have the results ready. Let's check the envelope safety factor. It's 2.1. It's even higher than the baseline. And for the first model frequency is still 44, 45 Hertz. That's good. The next step, we are going to determine some beat pattern that will help increasing the frequency. Why do we want to increase the frequency? Because later on we are going to optimize the thickness of those panels. By reducing the thickness of the panel, the frequency may drop. And if we create some beat pattern before that, it gives us more room to reducing the thickness and also the mass. To create the beat pattern, first we want to change the design space or package space a little bit so that the beats will only within the space that we want. I'll do me a simple cut here. Cut off this. I want to simplify the imprints here before cutting the piece. Okay, now I can cut it. Okay. So now all the brown pieces are the design space. I want to only select a few pieces to be design space, but other pieces are not changed. Here I can multi-select only these three pieces I want to create, where I want to create the beat pattern. And here I can specify whether I want a linear bead, circular bead, or radial. I want a linear bead in vertical direction, and I can change the icon here very easily, so the beads will be up and down. Similar for this panel and this panel. I want to rotate it 90 degrees. Also, because the battery will sit on this plate, for this panel the bead can be only downward, so I can enforce that by this draw constraint. And now with this setup, I can run the topography optimization to create those beat patterns. Here you can select topography and maximize stiffness. And there are some beat parameters that you can constrain. And for the objective, I want maximize frequency. And I need support from it. And with this run click, it will create an optimized beat pattern for me. This is with beat pattern created. You can see some pattern, some beats here and here. We can check the performance of it. The first frequency is now 48 Hz. I have more room to reduce its thickness. Now I want to merge the pieces together so I can do the next thickness optimization more easily. Something like this. Now I'm making all the pieces design space so their thickness can change. And I can run the gauge optimization to determine what is the optimized thickness or sufficient thickness for this. You can select gauge optimization, minimize mass, and here you can specify the minimum and maximum thickness for each part. And the minimum safety factor and the first frequency, I want it to stay about 40 Hz. And with the run click, it can optimize the thickness for you. This model has the optimization result ready. With this click, I can review the result. You can see the first mode is about 40 Hz, and you have the thickness with this colored coded. And we see most parts are stay below 2.7 millimeter. You can change the system here very conveniently. You can show the result in millimeter. But if this is made of a single piece of sheet metal, the thickness probably has to be the same everywhere. So I need to make some engineering judgment about it, and I say 2.7 is a good value here, because most optimized result is under 2.7 millimeter. Here I can change the thickness to 2.7, and then can perform a verification check on this final design. Here I'm comparing three models. The first, very left, is baseline original design, and the very right one is optimized design. I can compare their results very easily by this compare result button. You have a table for that. You can see for the worst load scenario, load case Z, this optimized design still have safety factor of 1.7, stay above the requirement. But the mass compared to the baseline, it reduced from 2.6 kilogram to 1.7 kilogram. That's 35% reduction. And the first model frequency is still above 40 Hz, which is 43 here. So to summarize today's seminar, I'm going to emphasize several points. Inspire is an optimization and concept generation tool that helps lightweighting and shorten the design cycles. And it is based on the technology that has 30 years of history and broad use across multiple industries. Inspire's topology, topography, and gauge optimization can help designers to develop structurally efficient sheet metal parts very quickly. Thank you for attending.